We introduce Can3Tok, canonical 3D tokenization and latent modeling of scene-level 3D Gaussians. Nowadays, 3D generation showcase the ability of freely exploring a generated 3D virtual world, which consists of rich visually appealing contents. But the problem is how to create such photorealistic virtual world. The most tedious way is to follow the traditional computer graphics rendering pipeline, where we ask professional artists to craft a bunch of things. They are called 3D assets, including geometry, lighting, materials, and textures. And after getting all these 3D assets, we can do the so-called rendering or shading process, which usually formulated as this very complex integration over multiplication of the 3D assets. As you can see, it is pretty painful, as all we just did for crafting and curating 3D assets is just get some 2D images or video frames of a single virtual avatar character. So a follow-up question would be, can we inverse this process so that we can really start from these rendered 2D images or video frames and end up with the 3D assets? Actually, there is an active research direction called inverse rendering. If you look at the formulation of inverse rendering, now we are starting from the integration result to infer individual components of 3D assets. However, this is a very ill-posed problem, as there is one equation but 4 unknowns, so there are infinite number of 3D assets combinations that can match the same rendering results. So can we relax the constraint a little bit? For example, we are still expecting some 3D representations, but they are not necessarily to be well-defined 3D assets. And the answer is yes. Here we have neural rendering, which can do 3D reconstruction with multi-view 2D images in a deterministic manner by optimizing neural networks such as neural radiance field, or 3D primitives with learnable parameters such as 3DGS. So both implicit or neural representations have nothing to do with well-defined 3D assets such geometry, lighting, materials. As long as we can always find a way to render these implicit representations into 2D and they look good, then we can treat them as generative objective. That said, we can train a 3D generative model on, for example, 3DGS, instead of 3D assets. Since we can always optimize 3DGS from multi-view images or videos, so data collection would not be a problem. Actually, 3D generation is never new. For example, there are many previous works for 3D object-level generation with all kinds of different implicit representations such as NeRF, triplane, and 3DGS. 3D object-level generation becomes feasible by training a 3D-aware image diffusion model on large collections of multi-view images paired with camera poses. These training pairs are obtained by rendering many 3D objects from diverse viewpoints. With sufficient coverage of common objects, the diffusion model learns to associate camera poses with corresponding rendered images. At inference time, we can provide the model with a novel camera pose, and the model is able to predict the corresponding rendered image. And after predicting a lot of different viewpoints, we can run neural rendering representations, such as NeRF or 3DGS for 3D reconstruction to achieve the object-level 3D generation from single view. When it comes to scene-level generation, it is no longer object-centric content creation, but requiring to cover much more 3D contents with large field of view. There are several common formulations. The first is to generate panorama, which basically 360-degree image generation. You can consider this as a way of pseudo-3D generation. The second option is still using image generation, but followed by 3D lifting, reprojection, 2D outpainting and then 3D lifting, all over again. Two representative works are Lucid Dreamer and Wonder Journey. The third option is to distill from a multi-view diffusion model such as Cat3D and then from image to 3D lifting. Therefore, the current progress of scene-level 3D generation is more about how to better leverage 2D generative prior. So 3D consistency would be a problem by natural. And the question is there any way to directly do 3D generation instead of 2D generation coupled with 3D lifting? So before answering this question, let's firstly recap image diffusion model. Ignoring all the mathematics details, forward diffusion process is required during training to add noise multiple times on a clean image until it becomes a pure noise. But the spatial dimension or size of an image is sometimes too large. Applying diffusion process on top of raw images could be expensive. So a common operation is to use an image encoder to compress an image into a low-dimensional latent and apply exactly the same diffusion process, but on top of latent domain instead of image domain. During inference, we inverse the above process so that we are sampling from the pure noise or Gaussian distribution, and then we pass this latent to our image decoder to recover the image. Our idea is pretty straightforward, that is. Can we design a pair of encoder-decoder such that we won't need to do some modification on the latent diffusion part? But at the end of diffusion process, we can directly decode out scene-level 3D GS representations instead of image. Therefore, the goal becomes how to train a 3D encoder-decoder to map 3D GS into a low-dimensional latent. We run 3D GS optimization on DEAL 3D VTNK dataset to get many per scene optimized scene-level 3D GS. However, we found that it is non-trivial to train such an encoder and a decoder because of several challenges. First of all, if we run 3D GS on different videos or multi-view images, we will end up with different numbers of per scene 3D Gaussians. For example, the number of 3D Gaussians for reconstructing a Lego toy is apparently much fewer than reconstructing a large-scale scene. And it is hard to train an unified encoder-decoder on varying number of 3D Gaussians. So the compromising way in our data curation, we upper bounded the number of 3D Gaussians during per scene optimization so that we will end up with the same number of 3D Gaussians for each scene. The second issue is the scale inconsistency. Different 3D scenes have different scales. Although it is physically correct, it is not good for network learning. Because we found that whatever the network architecture design is, the encoder-decoder just cannot compress many 3D Gaussians of different scenes into a unified latent space and correctly decode them back to the original 3D Gaussian representations. However, if we look back at the research of image representation learning for the past decades, a very common operation is to uniformly scale the spatial size of all the input images and normalize their RGB channels before feeding into a neural network for representation learning. And if we look back to 3D domain, all the different objects actually have same scale in object-level 3D dataset like ShapeNet, whether it is a chair or a laptop or an aircraft. Their sizes are the same. Inspired by this observation, we normalize all per scene optimized 3D Gaussians, including the 3D XYZ locations and the scaling factor of each 3D Gaussian primitive. And we rescale all the 3D Gaussians within a unit sphere. And then we found that the sum network design begins to converge by taking in these uniformly scaled 3D data. One more minor issue about 3D GS representation itself is its inconsistent reconstruction quality. If we take a closer look at the 3D GS reconstruction of a scene, and zoom in different regions, some parts are still blurry while some parts are quite clear and well reconstructed. And there is no benefit to feed all these 3D GS into an encoder-decoder and treating them equally. Therefore, we design an optional semantic-aware filtering process to remove 3D Gaussians outside the boundary of the main region or salient region, retaining only semantic meaningful parts. In this way, we can save the number of 3D Gaussian tokens to reduce the model size of the encoder-decoder. The one last issue is about network design of 3D GS encoder-decoder. We empirically found that 3D convolutional-based network does not converge on hundreds of scenes. For example, when the number of different scenes is larger than 500, a moderate-sized 3D convolutional-based network cannot correctly decode latents back to corresponding 3D Gaussians. In other words, 500 3D scenes can mess up the convolutional-based encoder-decoder. So we adopt a perceiver-based architecture as our autoencoder design. Each 3D Gaussian is treated as a token. We avoid using a naive transformer with only self-attention because the number of input tokens is very large, making self-attention computationally expensive. Also, we do not have an output query because 3D Gaussians are unstructured and irregular, so it is hard to find a regular-sized output query to decode latent into. Instead, we use fully connected layers at the very end of our decoder. This is one quantitative comparisons on DL3DV10K dataset with other network designs. During inference, we measure the L2 error between inputs and outputs, across all 3DGS attributes, including their XYZ 3D locations, rotations, scaling factors, spherical harmonics, etc. Note that all networks were trained with the same data after normalization. And our method is significantly outperforms in terms of recovering the input than other network design. We provide latent analysis showing why our method can better generalize on unseen inputs than previous methods. Here we use TSNE method to visualize the latent space. These four sub-figures showcase the latent patterns when we rotate an input 3D scene of different angles from 0 degree to 360 degree around different axes. And in latent space, the corresponding T-SNE visualizations all show closing loop patterns. And the network learns this spatial correspondence between input 3D space and latent space in an unsupervised manner as never supervised the network how latent embedding should change accordingly to match the rotation in input 3D space. And red dots in these two sub-figures show the visualization of latents encoded as the same 3D scene but with different rotations. While the blue dots are the visualization of latents of other 3D scenes. Ideally, the same 3D scene with different rotations should still be similar and close to each other in latent space, but dissimilar to latents representing other 3D scenes. In sub-figure E, our method can easily distinguish a scene from other scenes even the scene is rotated. However, the latent space of convolutional-based autoencoder is a mess. After the autoencoder design, we can now achieve scene-level 3D generation by firstly encoding many 3DGS reconstructions into low-dimensional latents. And then we can train a latent diffusion model on the latent space with paired text conditions. At inference time, we are able to sample from a normal distribution to denoise out clean latents conditioned on text prompts, and then we can recover the scene-level 3DGS with our pre-trained decoder. This is qualitative example showing text to 3DGS generation. Here, T denotes the number of denoising steps. These denoising steps were visualized by rendering from intermediate 3DGS from a fixed camera view. Another application is image to 3DGS, where we need to train an image encoder to map input images into the same latent space of our Can3Tok autoencoder. During inference, input images are encoded into latents and decoded into 3D Gaussians. Thanks for watching, and please refer to our paper and code for more details.